Good afternoon. I'd like to welcome you to the EMC Live webinar, EMC EMI Testing in Less Than 1 Second Using Very Near Field Techniques. My name is Helen Flood and I will be administering the webinar today. I'm the project manager at Interference Technology, the host and creator of this event. EMC Live is a new and innovative 3-day online event hosted by Interference Technology. This event highlights practical information and topics and will include roundtables, webinars, and videos on everything EMC related. Best of all, there is no charge to attend. Please visit the event website at www.emclive2014.com and plan on joining us for our other sessions over the course of the next 3 days. This webinar is presented by Ruska Patton. Ruska is the Director of Product Management at MSCAM, where he is responsible for the evolution of MSCAM's real-time near-field measurement solutions. He holds both a BSc and MSc in Electrical Engineering from the University of Saskatchewan. During this time at university, he was recognized with numerous IEEE awards and a Distinguished Research Scholarship. This webinar is sponsored by MSCAM, a world-leading developer of fast magnetic, very near field measurement tools. MSCAM provides real-time lab bench systems that are efficient and cost-effective and eliminate the need for anechoic chambers. They also offer accelerated time to market to liberate PCB engineers, antenna designers, and wireless engineers. A recording of this webinar and downloadable PDFs will be available on our website. Our webinar today will be interactive. We encourage you to ask questions at any time during the session. Take a look at your GoToWebinar navigation pane, the box you see in the corner of your screen. If at any time you have a question, we ask you to use the type box and hit send. To minimize or maximize the screen, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. At this time, I would like to hand the webinar over to Ruska, who will begin the presentation.
Okay, thank you very much. Yeah, as was mentioned, we'll be talking about EMC and EMI testing using what's called a very near field technique. And we'll see that one of the advantages here is the extreme speed of this technique. So first of all, we're going to give an introduction to the very near field. What does this term mean and how are we using it? And then we'll show how we've actually implemented a system that can do testing in the very near field. We'll explain some of the benefits to this approach, and we'll go on to show how this very near field testing can be used to give some prediction of the far field or the chamber-like measurement results. We'll show some other applications that aren't directly related to EMI and EMC testing, and then we'll finish the presentation. So first of all, MSCAN, we are a world-leading developer of very fast, very near-field measurement applications. This is based on an array of sensors that is a patented approach for MSCAN. This approach allows us to do real-time measurement of the fields directly next to the device under test. This real-time testing can give understanding of the near-field effects, the coupling, the distribution of energy across the board. Typically, these devices that MSCAN creates are all pre-compliance. So even though they may give some prediction of the chamber results, they're not compliance devices. Based on this array of sensors for the very near field, there's actually two different product lines. The first is what's called EM Expert, and this is the one that is related to EMI and EMC testing. This is the one that we'll be talking about this morning. There's another application for this very near field testing, and that would be for antenna measurement. The transformation to the far field in this case is done very accurately and can give results comparable to the chamber. This family of tools is called the RF Expert. Okay, so an introduction to the very near field. People might be familiar with the concept of far field and near field, and that general concept is shown on this slide here. We can see in the center of the device, in the center of the screen is the antenna radiating in all directions, and here we can see that the far field is given with some rules of rules of thumb. So these are approximations of the distance at which the far field region might begin. Essentially, this far field region is where the radiation pattern is kind of established and no longer changing with respect to distance. If we go within this region, then we enter what's called the near field. Inside the near field region, the emissions from the device are still interacting strongly. You're getting constructive and deconstructive interference, causing the fields to change very rapidly over a short distance. Inside this near field region, there's actually two different subregions. The first is the radiating near field. So this is where the energy has escaped the device under test, be it an antenna or circuit board. So it will eventually go into the far field region, but it just hasn't had that chance to set up and establish the fields in their far field conditions. So that radiating near field region is again given by some rules of thumb here. So these are approximations of where this distance might be from the device you're testing. Lambda, of course, is the wavelength, and the d in the d squared is the largest dimension of your radiating source. Now also in the near field, there's an area where the fields are not escaped from the device, but they're essentially stored energy. This is called the reactive region. And normally the reactive region is a place where you wouldn't want to put a measurement device. Because you're disturbing those stored fields, you're actually changing the device under test itself. Now what we've found is you can actually go into this region and get very good measurements of the distribution of magnetic field. So for antenna testing, this is quite critical. We have to account for these changes and essentially do a correction. In the EMC testing, what we'll see is essentially the magnetic fields are pretty stationary or static even when we place the scanner in this region. So we can get good measurements of the fields and hence the currents which created those fields. And this will allow us to essentially visualize on the PCB level what is going on in terms of induced currents or coupled currents or clock traces, that kind of stuff. So as an alternative to the very near field, of course, we have various far field measurement techniques. Shown here is the typical EMC chamber, semi-anechoic chamber. This is, of course, what we're trying to emulate, or at least this is what we're trying to measure at the end of the day. So we'll see that as an option to this, we can go back to the very near field and start doing measurements. And in fact, later on in the presentation, we will see that we can get very close to this type of measurement just from the very near field results themselves. Now, of course, very near field measurement itself is not something that we invented at MScan. Many people are already doing this. If you have a handheld probe, you will often place it very close to the device that you're testing and essentially be in that what we call very near field region. The difference is that a handheld probe typically is made very small so that it doesn't influence the device it's testing. And the downside is, of course, that it's very slow. To move that probe around and essentially sample all the fields in the different areas would take a long time. But if you went through this process, if you did capture all of these fields, it is possible to essentially recreate what we call the far field or the chamber test results. Now, of course, the very near field itself is the root cause of all those emissions. That's why essentially once you have that information, you can do that transition to the far field. Now, to do this, essentially we need a mechanism for doing the transformation, and that's where we refer to that extrapolation. Now we'll look at a very near field implementation, so something that can actually test in the very near field. And essentially this is the basic technology. So I mentioned before that we have an array of probes, and you can see here there's actually over 1,200 probes in this array, each one being essentially a near field probe, very similar to what you might be familiar with as a handheld probe. The difference here is that you no longer scan that single probe. What we do is we just electronically switch to that array and capture all of the fields over the entire measurement surface in sub-second time. Each of these probes is a magnetic field probe. So that means that we're sensing magnetic field very close to the device. And you can see in terms of frequency ranges, essentially it can run from 50 kilohertz all the way up to 8 gigahertz. Now, one of the limitations of the probe array is that the probe spacing is fixed. So we'll see that that is a limitation for essentially this switched array technique. But we do have a mechanism that can overcome this limitation and essentially reduce the resolution down to a fraction of a millimeter, as you see here. So we've just seen the array of sensors. The way this works in a system is that array is actually a passive array. So there's the 1,200 probes arranged in actually a grid over the surface. And those probes simply couple the energy and feed them into a spectrum analyzer. The spectrum analyzer is connected to a computer where you'll run the EMXpert software. And there's a small adapter that will then synchronize the switching of the probes and the triggering of the spectrum analyzer. So the combination of this system is essentially what does the entire near-field measurement. Once we've run some scans, what we'll identify from the device we're testing is a spectral emission. So essentially this is the same that you would measure with a handheld probe, or essentially the same frequencies that you would detect if you put your device into a chamber. So at this point, we're just identifying the frequencies that are coming from the device. Remember, we are measuring in the very near field, so the level of these measurements cannot be directly related to the chamber at this point. Once we've identified the frequencies, however, we can go and do what we call the spatial measurement. And this is really where the true value of the near-field array comes into play. You can see that at a given frequency, there's actually a distribution of that energy on the circuit board itself. In this picture, we're looking at the energy from a single frequency, 11 megahertz, which happens to be the fundamental frequency of a clock on this design. And you can see where the source of the emissions is next to this crystal. We can see how the energy goes into the microcontroller right next to the crystal. But we can also detect that that energy is leaking out into other areas of the board. We can actually see the paths that that energy is leaking through. That will allow us to understand the coupling mechanisms and also the mechanism that this might radiate into far field, causing an EMC or EMI problem. So you can imagine if you had access to this type of information early on in your design cycle, this is going to tell you exactly what it is that you need to address in terms of layout changes or other investigations, hopefully long before you actually take this design into a chamber and realize that there is a design problem. So what we're going to do is actually very quickly switch over from these presentation slides over to the software. I have this system set up next to me, and what we'll do is do a quick test on this scanner. So we will in fact see in real time how quickly this system can work. So right now we are looking at the software interface for the EMXpert system. I will open up a spectral scan. If we go to the settings here, we'll be able to see that it will be measuring from 10 to 110 megahertz with a fixed resolution bandwidth. So when we start this scan, turn on the device under test, and what we will see is we'll quickly go through and do the spectral emissions of this board. So we can see that it's identified several strong signals, 11 megahertz, 22 megahertz, 33 megahertz. So of course all of the harmonics. There's also some lower level signals in this mix as well. Now what this does is it identifies what frequencies we have to perhaps analyze further. So given that we've detected, say, an 11 megahertz signal, what we'll do is open up a spatial scan, and already set to 11 megahertz, 11.06 in fact. We'll make sure that the scan probes go over the entire scan area. And you can see, to make the selection of probes easier, I've actually imported the CAD file for this design. So I've imported a Gerber file. You can also do a JPEG if you don't have access to the CAD file, so you can simply take a picture of your device. So in fact, what we'll do is we will run this continuously. And what that'll do is allow us to make changes to the device and in real time see what the effect is. Sorry, my things here. There we go. Okay, so what we're looking at is the spatial distribution of energy on this board as it changes in real time. So on this board, we also happen to have a small capacitor. This is essentially a decoupling capacitor. I'll take that out. I'm trying to change the board too much there. And what I'm going to do is fix the scale. So really just to highlight the real-time aspect of this test system, as I put the capacitor back in, we will see an immediate drop of the near-field emissions. So of course, I already knew what the solution to those emissions was in order to drop it by over 10 dB. When you're working in your lab, you may have to do much more trial and error than this to actually find the real root cause and the solution. But you can see that essentially as quickly as you do make any changes to your design, you can evaluate what effect that has on your near-field emission levels. Okay, I'll just stop that. And then we'll go back to the slides. So again, that was just a quick demonstration. But you can see in just a few seconds we were able to quickly measure the device under test. Okay. Now what we'll do is just go through some of the benefits. So we've been using this type of scanner for many years. Many of our customers have given us feedback. We'll be able to see exactly how this can be used in practice. So the first one is changes in real time. Just as we saw there, if you are making changes to your design or if you are maybe changing the functional aspects, so maybe different operating modes or firmware changes. As soon as you make any change to your device, you can very quickly evaluate the effect that that has, at least on the near-field emissions. The other way that this is a benefit is in terms of intermittent events. So if you have maybe an emission problem and you can't trigger it reliably, what you can do is set up the scanner to run continuously and essentially trigger on that event, capture when that event does happen, and then even if it happens for a fraction of a second, we'll be able to capture some portion of it and then slowly build up an entire picture of the event when it does happen. So that will allow you to kind of get a snapshot of all the energy and where it's going when that intermittent event happens. So another strong application for this tool is in what we call A/B comparisons. So essentially, if you have a device where you've maybe done the full qualification, you have a near-field signature of this as well as a far-field measurement, and you've started making changes to your design for whatever reason. Maybe you have obsolete parts, maybe you want to do some cost reduction. Essentially, if you can make those changes and verify that there's no change in the near field, then you might have confidence to essentially self-qualify that device and not go through the full testing procedure again. Another aspect where that might be useful is just in doing some sample lot testing for production. Because you can do it in just a few seconds, you can sample devices from the production line and just make sure that there's no quality issues. Final aspect where you might be able to use this is in fault diagnosis. So again, if you have a board that's not working, very often the component or the section of the design that's causing you problems will also have a change in its near-field emission signature. So if you have a baseline to compare against, you can essentially place your new board or your failed board on there, do a comparison, and where you see large differences will most likely be the area where there is a problem. In fact, the example shown in this picture is a faulty soldering job on the RF trace. So the customer didn't know, couldn't track down where that problem in the RF chain was until they put the board on here, and they could see a significant difference in the emissions at the RF frequency at this specific location. You can also look at testing effectiveness of filters. First of all, even verifying that you're filtering in the right location. So you can see in this example, we have a power board on the right, and you have the functional side of the equipment, which is a mix of analog and RF processing on the left side. And if we look at the near-field emissions, you can see on the top that noise was generated in the power side and was coupling over to the digital side and even into the RF section of this board. So this can cause maybe problems in terms of performance of the device as well as emission concerns. Now, just to verify that in fact energy was coupling across those power lines, a ferrite was placed on there, and you can immediately see that was the proper solution. It dropped the energy that escaped into the analog side of the board by a significant portion. Now, this might not be a production-worthy change, although for some small runs that might be the best solution. But it does indicate what needs to change, and it did validate or at least verify the understanding that the energy was coupling across those specific lines. You could even take that further and look at one line at a time. Shielding and absorbers are an interesting one. Sometimes when you're using shields, what will happen is the energy will be reduced in that specific location because of the shield, but the energy is simply redirected to another area of the board. So you will have energy escaping out, radiated out of another area of the board, and essentially all you've done is displace your problem. So having the ability to look at the entire board at a given frequency and look at it in real time would immediately pick out whether or not you've done anything like just displace the energy. In the software, there's also the ability to do essentially a background subtraction. So you can look at the plots in terms of the difference between two scans, and essentially if everything drops in level, then you're content. If you've made some small increase or maybe a large increase at a specific location, that can at least direct your eyes over there, and you can analyze that problem further. Now, we mentioned that the fixed spacing of the array could be a limitation in some situations. What we've done is we've developed essentially a hybrid mechanical solution. So we'll take that fixed array and it will essentially put a small jitter on it, just by fractions of a millimeter, allowing us to create essentially a synthetic higher resolution array. And you can see what this will do is it can now take us down to individual trace level, identifying specific vias that are possibly coupling energy. And you can actually track this through different layers of the board to follow where your energy is coupling through the design. Now, so far we've always talked about the results in terms of the near field, and you can see that it does have tremendous value in the near field, but it does require someone that has a lot of experience in terms of analyzing these results and essentially making the correlation between what might be a compliance problem and what they see in the near field. What we're going to do is kind of highlight that concept a little bit more with a simple case study and just look at the correlation between the very near field and the far field. And essentially this will establish that link and give confidence that they can happen, that you can look at the near field and make some conclusions about the far field. So first of all, what we've done is just look at essentially a classical split ground plane problem. And you can see when put in a chamber at the various frequencies, there's a significant difference when one of the transmission lines goes across a split in the ground. What we did then was assume that the split had to remain in the design for whatever reasons, and look at some sort of mitigation. So we looked at combining those two grounds together, either with a short or with a capacitive connection. And we looked at various solutions, and essentially what we did is make a judgment just based on the near field. So here we can see the near field results with the solid ground, and then with the split ground. And then you can see just a couple of results have been shown here as an example, but there's the jumper reconnecting those two grounds in the center, and then the jumper reconnecting those two grounds at the edge. The center would be right underneath the trace that's going over that split, which is shown here in the bright red colors. What's very interesting is that from the near field itself, you can see that the jumper in the center is having a big improvement in terms of the near field levels. And in fact, the jumper, if it's placed at the edge of the board, seems to make the problem worse. So just from this quick near field analysis, we might be able to essentially reduce the number of samples or cases that we want to follow up on. So it doesn't tell us whether or not any of these will pass or fail in the compliance test, but it does tell us that if we have a split ground problem, and that can be identified, in fact, by looking at the near field as well, it also tells us what the best mitigation might be. So it doesn't tell us whether it's good enough, but it gives us some further idea of where to go in terms of a follow-up. Okay, so what we'll do now is we'll take that one step further. Rather than relying on the user to look at the near field and make those correlations with their basic understanding of near field effects, can we ask the software to make that step for us? Essentially, do the correlation. And the answer is that, in fact, you can do that. You can measure in the near field, and you can predict the compliance level measurement. Now, we use this quite extensively in the antenna measurement side of our company. The difference on the antenna side is that we would have access to the phase information in the near field. So in fact, we can get very accurate estimations of antenna measurements, radiated power, and patterns. In the EMC, we don't have access to the phase, so there's a bit more uncertainty in terms of the predicted results. But this is an example where you can see with that split ground problem, the predictions are within about 10 dB. So this has been improved over time, and with this software, they now say that they can get within 5 dB of the chamber results. Now, essentially the way that this works is you measure in the very near field with EMExpert. We export that near field data, and with this software we do a correction for the near field effects, which is known. We import that into the third-party software, and they do the transformation in the modeling to provide those chamber approximations. So that whole process takes between 10 and 30 minutes to run on your desktop with no other equipment required. So essentially this is giving you certainly one of the cheapest and also one of the fastest pre-compliance tools to essentially give you some confidence on whether or not your device is going to in fact pass or fail when it comes to the compliance testing. Okay, so if we look at this beyond just EMC, there's also applications for this very near field testing. A good example would be near field antennas. So normally antennas we would capture in our other product line, but for near field antennas they're not acting in the classical sense. We're really interested in what the strength of the fields are next to the device at various distances. So here you can see at 13.56 megahertz in a mobile phone which had a near field antenna, you can actually capture those fields and display the field strength that's right next to the device. Another type of testing is distortion or passive intermodulation testing. So because the device is very sensitive and also very linear, it's actually quite a good tool for measuring third harmonic distortion or some of these other things that are going to be very low with respect to the carrier. So in fact, in this testing, what we're looking at is measuring out of various antennas. And those antennas are shown with their fundamental transmit power. So with very, very strong transmit powers, 28 to 30 dBm, the system can measure those third-order harmonics down to about minus 120 dB with respect to the carrier. So that sort of sensitivity and linearity means that we can in fact use this for self-interference testing. So in this example, what we're doing is we're looking at the near-field emissions from the device, but not in the sense of a compliance test. Now we're looking at more in terms of self-interference or performance of your device. So if you have self-generated noise that is coincident with a received frequency, then obviously that's going to harm that receiver. In this case, we can see that noise was generated at 1.575 gigahertz, which happens to be right in the middle of the GPS band. Since that noise is generated whenever we have the camera on, you could imagine that the GPS performance of this device will suffer whenever you have the camera on. So now understanding where that energy is created and also how it couples through the design and what areas of the design seem to be radiating most strongly, that might give you some indication of either shielding, some absorber, or even redesigning to place the sensitive GPS receiver in an area that isn't radiating quite as strongly. Okay, so we're almost done. Essentially, we just want to look at the benefits of the system, and you can see this is kind of a neat picture. You can almost see the electromagnetic fields even coming down the cable and leaving the system. But certainly the strength of this system are the real-time peak hold capability for spurious events. That the fact that you can measure in less than a second means that you have access to a new way of testing your devices. You have this trial and error basis that's now repeatable, reliable, and sometimes a lot easier to do. Obviously this is not compliance data, but with the ability of other software to now take that near field and give an approximation, it does allow you to start making conclusions about whether or not your device will pass or fail. The final limitation that we see is we are limited a little bit in terms of the structure of the device. Obviously flat PCBs are optimum for this type of testing. If you have three-dimensional structures, there is some limitation there. And there we go. So certainly in terms of the test speed and an ability to give insight into design, we feel that there is certainly some value here for designers and even testers in the EMC world. Now I'll also point out before we end that a lot more information about MScan and EM Expert is available at the website. There are white papers and case studies that were essentially distilled down for this presentation. So if you had an interest in following up with more details, those are available on the website. Thank you.
Ruska, thank you very much for your presentation. Before we begin our question and answer session, I would like to make a call for final questions. Please feel free to enter any last-minute questions you may have in the navigation pane, and hopefully we'll get to them. In the meantime, Ruska, here's a question for you. Assume the colors in the spatial scan indicate amplitudes of emissions. Can the frequency range be limited or filtered for this display?
That's right. So the colors did indicate intensity. On the right, you could see that red was the most intense, blue was the least intense. The simple scans that I discussed here and that I showed in the demonstration were what we call single frequency scans. However, the software can run through a range of frequencies and combine those results together, giving you kind of a wideband spatial emission. And further, the software can then isolate or essentially slice through that data, and you can pull out one frequency at a time, or even analyze a single cell in the device and look at the spectral emissions based on location as well.
Ruska, can it be used to test emissions of small assembled products?
That's right. So when we mainly looked at the results here, I was always looking at the raw circuit board, and that's because we were mainly trying to push this as being early on in the design cycle, looking at root cause problems. But you can test fully assembled products. So in fact, if you are in a plastic enclosure, essentially that will have no effect on the emissions. If you're inside metal enclosures or some sort of shielded enclosure, what you'll see is not the board level emissions, but you'll see emissions coming out of seams and gaps in your device. If you have cabling that connects to your device, we might also pick up the emissions or the currents that are happening along that cable. So yeah, you can measure fully assembled devices as well.
Thank you very much. Here's another question for you. When testing at the very near field, does ambient noise still distort the results, or can the ambient noise be distinguished from noise from the unit under test?
Yeah, well, you saw from the testing that I did here, so I'm just sitting in our meeting room, so we're completely exposed to the ambient environment, and we didn't see any background noise. All of the emissions that we picked up were from the device under test. You can, of course, do a background scan just to verify that. Now, there is some situations where you will pick up ambient signals. If you're trying to be very sensitive, doing very sensitive measurements with low bandwidth and even with external amplifiers in the path of the system, it's possible that you'll pick up ambient noise, say, in radio stations or cell bands where there is strong signals. In that type of situation, you can do that background scan and subtract that out from your testing, or you may be required to go into a shield environment in that case.
Okay. Another attendee asks, if the DUT is kept upside down, will the pattern change?
Yeah, that's an interesting question. So for something like a two-sided design, essentially the top and the bottom will look very similar. If you have multi-layer boards and the internal either ground planes or power planes act as good shields for the EMC measurements, you will see a different signature on the top and on the bottom of your device. So if that's the case, what you can do is flip over that product and measure both sides, so that's not a problem. One further point to this is that on a multi-layer design, the internal layers of the board may also be conducting energy. Now those ones, especially at higher frequencies where the ground plane is a good shield, those cases we can't measure what's happening internal to the board. But if you think of it, those ones also are not contributing to anything to do with the emissions from the board. So where those internal layers become a concern might be at gaps in the shield, near the edge of the board, or when they transition to some of the surface layers. And in all of those situations, we would then be able to pick up the emissions whenever that occurs.
Thank you, Ruska. Another question. Does the EMI test bed measure both E and H fields, or is it H field only where E field is derived?
Yeah, right now this scanner only measures the H field. So it is possible to translate to the E field, although in the reactive region that's a very difficult problem. So we simply present the H field results in the software, and what that essentially correlates to is the currents on the board. So for board level analysis, the H field is probably sufficient. For doing the transformations to the far field, you can see that having only one of those components probably impacts the accuracy to some degree as well.
Okay, great. One more question here. How do you calibrate the single probe?
So, in fact, ironically, the single probe is in the array, at least an individual probe in the array is calibrated with a single probe. So we will use essentially that handheld probe technique. We have a robotic positioner which will move a single probe over every element in the array and very accurately position that single probe so that we can in fact measure the response of every single probe. And that data is essentially our calibration data. So we know not just the probe response, but also all of the internal losses inside the scanner. So when you turn on what we call probe compensation in the software, essentially all of the variations from manufacturing or from differential path lengths are taken into account so that the fields are then given very accurately at that probe location.
We're almost out of time. We have a couple minutes left, so I'm going to ask another question. I want to thank our audience. We're getting fabulous questions coming in, and we'll continue to feed them as we can with the time allowed. Ruska, for you, what level of sensitivity can be achieved, and how would that translate, say, to dB microvolts per meter at 3 meters?
Okay, so we saw the one slide that touched on the sensitivity, and we also mentioned this when we talked about the desense or self-interference problems. The way we've characterized the sensitivity in that case is a little bit different, and we've done it in terms of the conducted power in a microstrip. So if you have a conducted power in your microstrip of minus 145 dBm, we'll be able to detect the magnetic fields from that microstrip. Now it is a little bit frequency sensitive, so it's not that sensitive at all frequencies, but it gives you an idea that we can pick up the fields from extremely low level conducted energy. In terms of the EMC, or the compliance testing, this is many orders of magnitude lower than any sort of emission that would cause problems in a compliance setting. So the sensitivity in the near field can't be directly translated to a voltage in a 3-meter test setup, but if it were even close to failing in the chamber, we would probably be about 60 or more dB more sensitive than is required to pick that up in the near field.
Thank you so much, Ruska. We've received so many thought-provoking questions, more than we can get to today as our time is up. But I will ask that you please refer back to the event site where we'll post answers to all of these inquiries. Ruska will be providing the answers for us. Please feel free to email us at info@emclive2014.com with any more specifics, and we'll direct you accordingly. Also be reminded that a recording of the webinar will be available on our website next week, and a link will be sent directly to you. Our thanks again to Ruska for his time today and the time he will take in answering your questions, and to you for attending. Don't forget to check the website for any additional webinars or roundtables you would like to attend this week. www.emclive2014.com. Again, thank you, Ruska, so much.
Thank you.